the previous video, you will recall that we talked about the confidence interval for the difference of two means, and we used this example with generic batteries and WC energy batteries. And what we came up with was the following when we constructed the confidence interval. We talked about the sampling distribution for the difference of two means, and then we took a look at the actual confidence interval, and our confidence interval looked like this, and we had a confidence interval that went from negative 0.17 to positive 37.35, and we decided that we're 95% confident that generic batteries last anywhere from 0.17 minutes less to 37.35 minutes more than WC energy batteries. Well, we're going to follow that up with a hypothesis test for the difference of two means, and we're going to use that same context. So to start out with, we are going to start with the following null hypothesis, H naught, and we think that mu of generic minus mu of WC energies is equal to 0. In other words, there's no difference, versus the alternative, which is mu generic minus mu WC energy, is greater than 0. In other words, we believe that the average lifetime of the generic batteries exceeds the average lifetime of WC energy batteries. So the next thing we're going to do for this hypothesis test for the difference in the means is to calculate the test statistic. And the test statistic looks like this. We take the difference in our sample means minus the difference in our hypothesized means over the standard error. You will notice that the standard error is the same standard error that we used in the confidence interval for the difference of means, and the conditions are also the same conditions that we checked in the confidence interval for the difference of means. And since we used the same scenario and the same data, we're not going to repeat that here. So we'll go ahead and calculate this test statistic. It is a t-distribution, and the what did we have first? We had the generic batteries first, so the sample mean for the generic batteries was 206.017 minus the sample mean for the WC batteries, 187.433, minus the hypothesized difference of 0. That hypothesized difference is typically 0. It's not always 0. Your calculator defaults to 0, so if it's something other than 0, you won't be able to use the built-in function on your calculator. And the standard error for the generic batteries, the standard deviation for the sample is 10.3. We square that, divide by the sample size of 6. Plus, for WC batteries, the standard deviation is 14.61. We square that, divide by 6. And we go ahead and calculate this, and this turns out to be 2.55. If you had reversed the alternative hypothesis, instead in saying mu g minus mu WC is greater than 0, you could have said mu WC minus mu g is less than 0, effectively meaning the same thing. When you calculate your test statistic, you would have gotten a negative 2.55. But in the end, you still would get the same value for the p-value. The degrees of freedom, as you know, comes from some really complicated formula. I would recommend you use what the calculator gives you, and I will show you in a moment how to get that in the p-value of 0.0157. And under most circumstances, with a p-value that small, we would reject the null hypothesis. Now, how do we interpret this p-value in context? I'm going to say it, but I'm not going to write it down. If there is no difference in the population mean lengths of time that the batteries last, then there is only a 1.57% chance of getting a sample mean in which
the difference in the sample means is this large or larger. Since this is so unlikely to happen by chance, we would reject the null hypothesis and conclude that generics have a greater average life than WC energy batteries. And how to do this on the calculator. So if you recall from the previous video, this data was in the form of lists. So the first thing you're going to do is put that data into lists in your calculator. It does not matter which lists you put it in. So I happen to put the WC energy batteries sample values into list 4 and the generics into list 5. And I want to do a 2-sample t-test. So 2-sample t-test. Let's see, 2-sample t-test. I'd have to scroll through this. There it is, 2-sample t-test number 4. I am going to use the actual data, so I select data. Now, we do have to pay attention to which lists we have our data in and make sure that that corresponds to the correct alternative hypothesis. So I happen to have the generics in list 5, and I happen to have the WC energy batteries in list 4, and I'm going to count each of those values once, and I am basically saying that I think that the population mean for generics is greater than the population mean for WC energy, so I'm going to use mu1 greater than mu2, which is the same as mu1 minus mu2 is greater than 0. Again, if you're offered the option to pool or not pool, the answer should be no. The only reason that you would do this is if you had reason to believe that the population standard deviations were equal, which actually involves another test, which we are not responsible for in this class, so we're going to skip that, and we're going to go right to calculate. And you will see that we got a test statistic of 2.55 and a p-value of 0.0157, and the degrees of freedom from that really complicated formula of 8.98. And you got the sample mean and the sample standard deviation for both samples, and there's a whole bunch of other information, sample sizes down at the bottom. So if I were doing this on a quiz or a test, I would actually put the data in my calculator first, particularly in this situation because the sample sizes are so small, and plot the data, look for skewness or outliers, do the test, and then go back and actually show my work right here. So that is it for a hypothesis test for the difference of two means. If you would like a little bit more practice, there's a few examples coming up. I just want to review. What should you be checking? You should have 2 random samples. Both the populations both the samples should come from normal populations or should be at least size 30 so that we can be comfortable that the sampling distribution of the differences is approximately normal. We should have independence within the sample groups, i.e. the 10% condition, and then we should have independence between the 2 sample groups. So if you'd like to at this point, I suggest you pause the video and you go ahead and you take a look at problem number 2, work through that, and then you can unpause the video and check your answers. So this scenario is about the size of longleaf pines in 2 halves of a forest and how their mean diameters compare, and they want to know if the samples provide evidence that one mean is different from the other or greater than the other. So our null hypothesis would be that the mean from the southern is equal to the mean from the northern or their difference is 0. The alternative is that the mean from the southern is greater than the mean from the northern, or mean southern minus mean northern is greater than 0. If you reversed the alternative hypothesis, mean northern minus mean southern is less than 0. You can check both of your condition. You can check your conditions for both samples here. Both sample sizes are at least 30, So we have met the normality condition. Both samples were randomly selected and therefore reasonably independent of each other. I think it's reasonable to assume that 30 trees are less than the corresponding halves of the forest, or 10% of their corresponding populations. And here's how you calculate the test statistic. You would get a t-value of either positive or negative 2.62 with 55.7 degrees of freedom. Turns out to give you a p-value of 0.0056, which is relatively small compared to any reasonable level of significance, so we would reject the null hypothesis. And as such, we have significant evidence to suggest that the mean population diameter of longleaf pines in the northern region is greater than that in the southern region is greater than that in the northern region. If you would like to do yet another example, you can pause the video here and do problem number 3, and then I will go through the answers with you when you're done. In this particular experiment, the subjects were either treated to a calcium pill or a placebo, and then they measured the average decrease in their systolic blood pressures. And the mean here refers to, the population mean here refers to all subjects that are similar to the subjects that took part in this experiment if they were to take the calcium here. It is not a reference to the subjects in the experiment. We know that information. What we're doing here is we're doing a hypothesis test about the rest of the populations if they were to take calcium supplements versus placebos. So the null hypothesis is that there is no difference in the average change in blood pressure between the calcium and the placebo treatments, and the alternative is that the mean decrease for calcium treatments is greater than those for the placebo treatments. And remember, that refers to all subjects that might eventually take these treatments. The 10% rule here does not apply because there was no random selection from the population. These were volunteers. Remember, that 10% rule assumes that you're sampling without replacement, but we're not in this case. They're actually volunteers. So we can't invoke that for the independents. However, we can deal with that in another way. So let's talk about the meeting the conditions. Random assignment of the subjects to treatment groups was used, so we have met the random condition. We can assume independence between the groups because of the random assignment. I believe we can also assume independence within the groups because of the random assignment. And if you plot both sets of data, there's no skewness or outliers in either sample. However, the normal probability plot of the calcium group is not entirely linear. So we, for the sake of the problem, are going to assume the normality of the sampling distribution. We go ahead and we calculate the test statistic, the sample mean from the calcium group minus the sample mean from the placebo group, and we subtract the hypothesized difference of 0 divided by the standard error. We get a test statistic of either 1.604 or negative 1.604 with 15.59 degrees of freedom, a p-value of 0.064. So this seems to be some evidence that the calcium treatment works, although it's not less than our typical p-value, alpha value of 0.05. So based on this p-value, if alpha is 0.05, we would not reject the null hypothesis. Therefore, we have not found significant evidence to suggest that calcium helps reduce blood pressure more than a placebo. However, if you had used alpha of 0.10, then you would make the opposite conclusion. And that is it for hypothesis testing for the difference of two independent means. The last section, we will talk about what if the means are not independent of each other, so for example in a matched pairs experiment.